Hey, Physics 20s, Mr. Dukley here to talk to you about force of gravity and normal force. Normal force looks a little bit weird. It's big F subscript N, but still the same thing. So if you're not already there, get out your yellow work booklet. It is Unit 3, Lesson 5, page 81. And obviously your data sheet and your calculator and everything else you need, but pop it all out and we'll get started right away. Cool. So we have already kind of mentioned this definition, but force of gravity and weight, but we're looking at this in a bit more detail here. So note that in physics, force of gravity and weight mean the exact same thing, and we talked about that way back when. So for example, if I am an 800 Newton person, that means that my force of gravity is 800 newtons. Now you may remember this formula, putting it all together. So weight is equal to force of gravity. Now, if I were looking to calculate my force of gravity is my mass times the acceleration due to gravity on the surface of the Earth. Now, there's something a little funky going on here when we look at acceleration due to gravity on the surface of the Earth. We are now calling it the gravitational field strength measured in newtons per kilogram. More on that in Unit 5, but for now, just note that acceleration due to gravity is the same thing as gravitational field strength, exactly the same thing as gravitational field strength. It's all lowercase g is what we're looking at there. And you know on the surface of the Earth, it is 9.81 meters per second squared. Or if we're using our new units, we would say 9.81 newtons per kilogram. Cool, so that newtons per kilogram, if you're looking for a bit of a challenge, see if you can figure out how newtons per kilogram is exactly the same thing as meters per second squared. See if you can, that's a good challenge actually. See if you can figure that one out. Cool. So one important difference to note is mass versus weight. So mass, remember, is how much stuff you're made out of, how much matter you have. And that doesn't really change ever realistically. I mean, over a period of years or something, if you gain or lose weight, or if you're growing or shrinking, that doesn't happen as often. But your mass stays the same, right, for all intents and purposes. But your weight can change drastically, right? So if I had a 5 kilogram mass here on Earth, where the gravitational field strength is 9.81 newtons per kilogram, it's going to be pretty significant. We do 5 times 9.81. Don't actually know what the answer is off the top of my head. Let's grab a calculator. 5 times 9.81, 49.05 newtons, right, is my force of gravity for that 5 kilogram mass. But if I take that exact same 5 kilogram mass and I put it on the moon, so I do now 5 times the acceleration due to gravity on the moon, so 5 times 1.6, that works out to be 8 newtons. No sig digs or anything here is what we're talking about, but a significant difference. So the weight absolutely is very, very different, knowing that the weight is force of gravity, but the mass stays the same. Cool. I've already kind of mentioned this. I have a 400 Newton object. What does that actually mean? Well, it means that my force of gravity is equal to 400 newtons. Now, here's an important question. The next part of this is, well, if I knew that an object's weight was 400 newtons, could you figure out that object's mass? How could we figure out that object's mass? If you're thinking to yourself, oh, well, we just use our formula we talked about a second ago. Fg is m times g. We can rearrange and solve for mass. It's the force of gravity divided by that gravitational field strength, or acceleration due to gravity. Perfect. So if it tells us it's a 400 Newton object, that means that's its weight. That means it's its force of gravity. And we can use the force of gravity to figure out mass. Cool. Okay, something important for all vertical questions, every single vertical question. It's not going to tell you about the force of gravity, but you need to know it's there, right? So lots of questions. A rocket ship accelerates upwards with acceleration of 27 meters per second squared. What is its applied force? or what is the force from the thrusters? We could ask that question, no problem. We would have no idea if we didn't include the force of gravity. We have to include Fg, regardless of whether or not it tells us, right? So have to include Fg. So let's check it out in a bit of an example. We've got a 350 gram mass. Okay, that's cool. It tells us right there it's a mass. I'm going to label it anyways. It's being pulled upwards with a force of 8.7 newtons. So it's being pulled upwards. I'm going to call that applied force. It is moving at a constant 6 meters per second. You remember why I'm underlining constant just as much as the 6 meters per second? Constant tells us something very, very important. The fact that it is constant velocity tells us that the net force is actually equal to 0. So that constant, I would argue probably for this question, more important than the 6 meters per second. And then the question is, what is the force of air resistance? So let's just label that FAR. Now, you may remember, whenever we are dealing with a problem where there's a whole bunch of different forces, it really comes down to 2 or 3-ish things. So one thing we can do to really help organize our thoughts is we can draw a free body diagram. So I've got a rocket ship. You know what? I'm going to make it a triangle today. So I've got my rocket ship, and then I have, let's see, an applied force pulling that rocket ship upwards, and that applied force is 8.7 newtons. And then we've also got a force of air resistance, resisting that's always opposite to the motion, so that one's going downwards. You'll notice, right, if the net force is equal to 0, and these were the only two forces, they should be the same size, right? But you'll notice that the applied force is drawn a little bit bigger because we also have our force of gravity going downwards. Perfect, force of gravity going downwards. So that's one thing that we always kind of keep coming back to is these free body diagrams. And you know what? I'm just going to finish something off on this free body diagram. My force of gravity, I don't know what that is yet. I know it's there. It's a vertical system. I know it's there. I can figure it out. It's just m times g. So we might as well do this off to the side. So mass, oh, I don't really want grams. So we should probably change that into kilograms, our standard physics units. So 0.35 kilograms, and then nowhere in the question does it tell us what lowercase g is, our gravitational field strength, but assuming this is right close to the surface of the Earth, it's 9.81 newtons per kilogram, and I'm using that new unit very specifically here, because look what happens. I get kilograms divided by kilograms. All we're left with is newtons, which is an appropriate unit for force. So my force of gravity, when we plug all the numbers in, let's see, 0.35 times 9.81 is 3.4335 newtons. Cool. So free body diagram's now complete. We've even added a bit of stuff to it. The other things that I want to come back to is Fnet is mass times acceleration, and if the acceleration is 0, the net force is equal to 0. We've already talked about that, right? So if Fnet is equal to 0, acceleration is equal to 0, and vice versa. So that's one important thing. The other important thing that we kind of look at here is net force is the sum of all the forces. So that's going to be my applied force, which I know a bit about, plus my force of gravity, which I know a bit about, plus my force of air resistance. Now, one really, really, really important thing, when we're adding all of these up, applied force plus force of gravity plus the force of air resistance, we didn't take into a direction into account. Now, this is a 1D problem, so you know what we'll do? We'll say up is positive and down is negative. Just our standard kind of thing there. So we know that this force of gravity, we've already calculated it. I'm just going to put a little negative in there. You could also, instead of doing plus a minus, you could just say minus force of gravity. Either way, it's going to work out to the same thing. So let's rearrange. Let's solve for our force of air resistance. So my force of air resistance is going to be equal to my net force minus my applied force plus my force. Oh, I'm kind of combining two different ways to do it. Let's go back a split second. I'm going to say minus my force of gravity keeping in mind that my force of gravity is downwards. That's why I was thinking it was plus. You subtract a negative, it's plus. So either of those two ways would be A-okay. So then we go through and quite simply we plug in the numbers. So net force was 0. I know that because it's a constant speed, minus my applied force, which was 8.7 newtons upward, so minus a positive number, and then minus my force of gravity, so minus negative 3.4335 newtons, and I end up with my force of air resistance being equal to, got to plug it in here, should be 5.3 newtons, and when we plug this into our calculator, it should come out as a negative number, which means down, right? So negative in the calculator will mean down. Cool. So that's not too bad. Let's put a circle around it. Big idea with this one is for any vertical system, don't forget you need to include force of gravity. Have to include force of gravity. Cool. The next big thing we want to talk about is normal force. So normal force is the reaction force when any two surfaces are pushing together. This is quite the picture, this guy doing wall push-ups here. And we've talked about normal force a little bit here. So we've talked about it as we're standing or sitting, right? I am standing in the front of the classroom right now. Force of gravity is pulling me downwards, but I'm not accelerating downwards. I'm not even moving anywhere. I'm literally, here's me, just standing on the floor, right? Just standing there. So I am applying a force downwards on the floor. The floor is applying a force upwards on me. So my normal force is the force that the floor is applying on me that's holding me upwards, preventing me from going through. Now, if we want to get a little bit more specific, normal force doesn't have to be on the floor or on the chair. It's any two surfaces pushing together, and it's resisting one surface passing straight through another. So we see this guy's probably got two normal forces, one on the floor where his sneakers are that are holding him up, and one on the wall that's preventing him from just falling face forward through the wall. Cool. And I should also note with this, well, I mean, a couple things to note. One, the normal force is measured by a weigh scale. So you'll notice that weigh scale is in quotation marks. Weight means a lot of different things depending on who you talk to. For us, remember, it's measured in newtons. So measured by a weigh scale. This one probably has pounds or kilograms or something like that, the one that this person is on. But it's all just based on the force of gravity. Right? So normal force is what you would see on a weigh scale if you're standing on a weigh scale, sitting on a weigh scale, anything like that, but measured in newtons. The other thing that we look at is normal force is always, 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 always perpendicular to the surface. So if it's me, and I'm standing on the surface like this, I'm a circle all of a sudden, my normal force is at 90 degrees to the surface. What about the skier over here on the left-hand side? So this skier, the normal force, 90 degrees to the surface, is at a bit of an angle like that, right? So there's a big 90 degree there. The ladder, right? It's got two different normal forces. It's got at the bottom of the ladder. So it's got a normal force like this, because we are, I'll just highlight it in black here. We are 90 degrees to the surface being the ground. So 90 degrees there, or I'll highlight it black on the side if we're thinking about this one. The surface is right here, so my normal force still 90 degrees, Fn, still 90 degrees to the surface. So always, always, always perpendicular or 90 degrees to the surface. Cool. What about in this kind of situation? So this person is it looks like they're doing a high jump competition on rollerblades. I hope there's something to land on them. There's that landing flat hurts so much. But is there normal force acting on this person? That's the question, right? So if normal force is pressing together between two surfaces, there's not really a surface that she's pressing on. So Fn, when we're in free fall, like this person is, in free fall, is equal to 0, right? There's no surface for this person to push against, right? Or to push back against her. When she hits the ground, that's another story. But in that particular freeze frame, the normal force is equal to 0. There's no squeezing between two surfaces. Cool. So let's check this one out, and let's keep in mind that the weigh scale reading is Fn. And I'm jumping ahead a little bit here, so let's check this out. So we've got a 700 Newton person. So right off the bat, we should recognize that that is a force of gravity. So 700 Newton person is on an elevator that is accelerating downwards. I have a feeling that's going to be kind of important. The fact that it's downwards and the fact that the acceleration is 5.8 meters per second squared. Cool. So she's on a weigh scale. What is the reading of the weigh scale? Or in other words, what is her apparent weight? And I don't think I actually mentioned that term before. So apparent weight is your normal force. I'm gonna add that right here. Apparent weight, which really means how heavy you feel. So even before we jump into this example, think about the last time you were on an elevator. Think about it like if the elevator has an upwards acceleration, how do you feel? Typically feel a little bit heavier, right? If the elevator is accelerating downwards, how do you feel? Usually a little bit lighter. Right? And if you've never noticed this before, next time you're on an elevator, this is one piece of homework for you. Next time you're in an elevator, try it out. Really focus on how you feel when that elevator is accelerating upwards and accelerating downwards. Okay. So let's go through and let's start to figure a few things out here. Let's start to figure a few things out. One thing that I always like to do, start with a free body diagram. So I'm thinking about that person. That person has a force of gravity going downwards, which I'm going to make very randomly this big, and that's going to correspond to 700 newtons. Cool. Now, I know that there's a normal force, and I know that the normal force, if the person is standing on a flat elevator floor, has to be directly upwards. But I want to think to myself, is it going to be bigger or is it going to be smaller? So I'm just going to draw the acceleration vector off to the side. So my acceleration is downwards. Which direction is my net force then? Draw my net force off to the side as well. Net force also needs to be downwards, because if the acceleration is downwards, the net force is downwards. Okay, so now let's think about this for a second. If the net force is downwards, that means I need a bigger force down than my up force. Or in other words, my normal force has to be smaller than my force of gravity. Cool. So I've got this kind of figured out all right here. Let's go through and let's start trying to solve with our two standard things. So I've got two big ideas. I've got my net force is equal to mass times acceleration. So I think we could even go through and solve for this right now. So mass, oh no. Do you see a problem here? Yeah, I see a problem. We don't know the mass. Shoot, any ideas on how we can figure out the mass? If you're thinking it's got something to do with that force of gravity, you are spot on. So we've ran into a bit of an issue. I'm just going to erase. You can find a different spot on your page. That's a-okay too. I'm going to first find the mass. We've run into a roadblock, so let's find mass. Let's get over that roadblock. So Fg is equal to m times g. So I know the mass, rearranging for the mass, must be Fg over g. Excellent. And Fg was 700 newtons divided by 9.81 newtons per kilogram. And you'll notice we're using newtons per kilogram, that same unit, a little bit more, because look how much nicer it is to deal with for all this stuff. So now I know that the mass is going to be equal to whatever 700 divided by 9.81 is. I think that is 71.36 kilograms. 71.36 kilograms. Cool. Now I think we can go back and we can start to look at, I'm even going to kind of label these. Number 2, I can start to go through and I can look at F net is equal to mass times acceleration. Nice. We can go through and we can look at this. So mass, we now know, is 71.36 kilograms. And my acceleration was, where is it? I didn't write it out. 5.8 meters per second squared. So go ahead, plug that into your calculator, put it on pause if you need to. But let's go through. I'll do it as well. 71.36 times 5.8. So when I plug everything in, and we'll make sure 71.36 is rounded answer, so we'll make sure we use the whole 71.35575.943, the whole entire thing, we end up with 413.86 newtons. And I'm going to take that one step further and say down. And I know it's down because what direction is the acceleration? Down. Right? So 413.86 downwards. Cool. My third and final step that I'm looking at here is dealing with that other formula we keep coming back to. The net force is the sum of all the forces. So that's going to be my normal force plus my force of gravity, keeping in mind that my net force and my force of gravity are downwards, and we should probably set a convention. So let's go through and say, let's go up is positive. We'll use our regular standard direction conventions. Cool. So I'm looking for my normal force, Fn. Let's see, that's going to be my net force minus my force of gravity. Cool. Net force minus my force of gravity. So my net force, I just figured out, was negative 413.86 newtons. I'm going to subtract from that my gravity, so minus negative 700 newtons. So we're paying very close attention to directions in all of this. And my normal force, when all is said and done, we plug everything in, it's equal to positive 286 newtons. Just let me double check that one real quick. 286 newtons, yes, which is 286 newtons upwards. So Fn 286 newtons upwards. Now when we think about that, the person's normal force of gravity is 700 newtons. They're going to feel like they're significantly lighter or like they have significantly less weight, right? So their apparent weight, 286 newtons upwards. Cool. Now let's just check there. Does that match the prediction that we had at the very, very beginning? So back to our free body diagram, we predicted that Fn was going to be upwards, and we predicted that it was going to be smaller than the force of gravity. So that matches our prediction. Very, very good. Very nice. Awesome. So last thing that I want you to do here, put the video on pause in a second and see if you can figure out the weight, remembering that weight is force of gravity, and the normal force on each of these situations, remembering that normal force is apparent weight. So how would this person standing on a scale inside of an elevator feel if they were moving upwards at a constant 4 meters per second, accelerating upwards at 5 meters per second squared, accelerating downwards at 6 meters per second squared, and then accelerating downwards at 9.81 meters per second squared. So go ahead, take a minute, put it on pause, try and figure this out. Go for it right now. Alrighty, so hopefully you had a moment to think about this one. So the very, very first example on the left-hand side of the screen over here, one thing that's really, really important, this is a constant speed or a constant velocity that we've got over here. It's not an acceleration, and I know that because it's meters per second, not meters per second squared. So anytime I see that, I know that F net is equal to 0, and so my force of gravity is going to be the exact same magnitude as my apparent weight or normal force, just in the opposite direction. So I'll summarize that down below. Fg is equal to Fn. Cool. For the second example that we've got over here, so I'll just summarize that, F net equals 0. For my second example that I've got over here, the person is accelerating upwards at 5 meters per second squared. So this person's force of gravity, exactly the same size that it was in the first one. So I've got force of gravity going downwards. And then I need normal force. It's obviously going to be upwards, but bigger or smaller? So because the acceleration is upwards, that means F net is going to be upwards. That means we need a bigger upwards force than we have a downwards force. So in this particular case, my Fn is going to be greater than my force of gravity, and this person would feel heavier, right? They'd feel heavier if they were in this elevator. Okay, let's check out the next one. This person is accelerating downwards at 6.0 meters per second squared. So I'm going to start a free body diagram. I'm going to put the force of gravity being the same size, because this person's force of gravity from the left over to the right isn't changing at all. The normal force is what's really changing here. So they're accelerating downwards. That means that my net force must be downwards. That means that overall I need a larger downwards force than my upwards force, so my normal force has to be smaller than my force of gravity. Cool. Okay, and then the very, very last one, the acceleration is downwards, and we have that same force of gravity. So same size force of gravity as all of them. I'm at least trying to make that the same size. This one might need to be a little bit longer. But same force of gravity. That's a very, very, very particular acceleration that we've got there, 9.81 meters per second squared. That's the acceleration that everything falls at, and it's in free fall. So if you said normal force is 0 in this case, you're absolutely right, because this person is in free fall. And in free fall, there's nothing actually holding him or her up. Cool. So that is our lesson for this one, for our gravitational and normal forces. So check out the practice problems, see what you can do with them, and let me know if there's anything you need. That is it for now, Physics 20s. We'll talk to you again soon. Bye-bye.